specific area.
Speaker is Carlota Andres from École Polytechnique. She will talk about a numerical approach to calculate in medium emissions. Thank you.
So hi all. It's nice to see you all in person finally. So, well, I'm going to talk about this numerical approach that we developed with Liliana, Fabio, and Marcos, our student in Santiago 2 years ago to solve the medium-induced radiation spectrum. So, well, I don't think, do you hear me well? Okay, I don't think there is much need of an introduction here, but what we are going to talk today is just medium-induced radiation. So we will go back to the basics of jet quenching, and we will be focusing on this diagram here. So it's the idea that when a highly energetic parton propagates through the quark gluon plasma, it's going to interact with the medium, and that's going to produce extra radiation, this emission of gluons that we call medium-induced radiation. So I'm not going to go through the details on how we do these calculations, but I would like to highlight that we always work in these high energy limits. So the parton is highly energetic. And that means that in our calculation, basically all the transverse calculation decouples from the longitudinal one, and we emit a gluon that in our case today, we are going to consider it to be soft. So the energy of this gluon that we call omega is going to be much smaller than the energy of the quark. And this is basically the basic diagram of medium-induced radiation that, of course, it was computed many years ago. And what we are going to talk today is about the new developments in the calculation of this diagram that goes in the basics of any jet quenching calculation, even in Monte Carlo approaches. So, well, this is basically the result of computing this diagram. And this was developed already in the 90s by BDMPS. And this is our spectrum for the mission. So this is the spectrum differential in KT and differential in the energy of the angle. And this is always in this soft limit. So the omega is much smaller than the energy. And actually in this soft limit, the expression looks like quite compact. So we have here first the kernel, which accounts for what's happening in this part of the diagram. And I'm not going to go through the details of it. It's just to show you the structure of this thing. And then we have the broadening. So even this was computed 20 years ago. In the last year, there has been also, well, not in the last, but maybe in the last 10 years, there have been also developments about going beyond these soft limits, so allowing this omega to be larger. And that's something Fabio will talk about today. And this further complicates the calculation and gives a much complicated expression. So I will let the details for him afterwards. So even this formula looks quite simple. It's not such a big thing. The problem is how you numerically evaluate it. So the thing is that the broadening is given by this expression here, and actually that's not difficult to compute. You can compute the broadening without many problems actually, but the problem is the kernel. So the kernel is given by this path integral that we have here, and of course we don't like path integrals. We don't know how to evaluate path integrals. And here we see that solving this path integral for let's say for a potential of the medium that is more or less realistic is quite difficult. So basically in all these calculations, the medium information is given by encoding this n, that is what we call the density of the scattering centers, and this sigma, which is the potential with the medium. So the problem is evaluating this for a sigma that is kind of realistic, like a Yukawa or an HCl potential. And this has led in the past to have many approximations, so that you all know here. So for instance, we have GLB or AMI or the harmonic oscillator approximation, which are just different approximations, different ways of evaluating this kernel. And this gives you two very nice expressions that are analytic in some limits at least, and that allows you to capture many of the physical effects and understand a lot of things. But of course, they are not perfect because they are approximations. And it's very nice because in the last years, we have had like many new approaches that go beyond the usual approximations. So I have put here like in purple the approaches that are numerical, and in green the approaches that are analytical. And I will start with this first approach, but Karen Watt and Gail, that was actually developed quite a lot years ago, like more than 10 years. This approach basically solves this formula in an exact way, but for the integrated in KT. So it doesn't do the differential in KT. And it's basically a numerical method to evaluate the kernel. So we took this approach by Carlota and we extended in this fully resumed spectrum 2 years ago, which allows us also to do the differential in KT spectrum. And then very recently, Soren and Ismail also continue with this approach by Carlota and basically managed to do this for a potential that does not only have the correct ultraviolet behavior as the UCAVA or HCl, but also has the infrared correct behavior, and this potential comes from the lattice. So this is basically a numerical approach that allows you to evaluate the spectrum as it is exactly without any other assumptions. And then we have also very nice analytical approaches like the improved opacity expansion that goes beyond the usual expansions that we have before. So they are a little bit more accurate, but they're analytic and they are very nice to also understand physical effects. And this very recent paper from last week, where basically they combined improved opacity expansion that works quite well at large energies, large and intermediate energies, with something that they call a resume opacity expansion that works in the low energy limit. So they managed to have an analytical, semi-analytical expression for the spectrum along all the energies. So basically the Carlota approach that we also take and that Soren takes is based on solving this differential equation. And the idea is that the kernel is a propagator, so it satisfies a differential equation. So instead of trying to solve this very complicated path integral, we solve the differential equation, which is not straightforward, but it's much easier than solving the path integral. And you can do it for different potentials. And what I will show today is solve for this UCAVA that I have here on the right corner. So with this, we managed to basically put the approaches in different, in a plot. And what we have here is in purple is the full solution of the evaluating in this formula compared to different approaches. So we have here the typical first opacity result, the GLV, and then we have the improved opacity expansion that, as I said before, it works very well at high and intermediate energy. And then we have some formula that we derive that is just the low omega limit of the spectrum that is semi-analytical, that at some point breaks and it cannot work at high energies. And this is something we did last year. And this is very nice because it allows us to understand a little bit the physics and the different energy regimes. And then very recently, last week, this paper was put on the archive where basically they have this black curve that approximates the black dash one that is very difficult to see there. The black dash one is the full solution, the numerical one that we compute in the one that we had in the previous plot. And then the black that is not dash, the solid one, is the one that uses the analytical approaches. And as you see, it works very well in all the energy regimes, and it combines two different approaches, one at low energies that is basically the same low omega curve that we have here, this dot one, and then the high energy one that is the improved opacity expansion. So with this, we have arrived to the point that more or less we have an understanding of the spectrum, but of course this was done for static media, and this is not what we want to do next. The thing we want to do next is to move to longitudinal evolving medium to try to at some point do phenomenology with these things. Instead of doing phenomenology with the harmonic oscillator, try to use these new tools to do phenomenology. So I will talk about this during the rest of the talk, and also Subix will talk about a longitudinal evolving medium in the context, in his case, of the harmonic oscillator approach. And also he will do, he will also use rate equations. Here I will just focus on this spectrum. And I would like to highlight that what we are gonna talk about is just longitudinal evolving medium, because as I said before, in this kind of approaches, in this derivation of the BDMPS formula, we work in this high energy limit. So we don't have basically any information about what happens in the transverse direction. And I mean with transverse to the propagation of the quark, or the emitter. And if you want to encode these things that happen in the transverse direction, you need to basically go beyond this high energy approximation that we usually call aconal approximation and allow for subaconal corrections. And that's actually quite difficult calculations to do, and both Andre and Joao will talk about this in the context of including median evolution, like dynamic flow in the transverse direction, and also allowing the median to be not homogeneous in the transverse direction. So, well, the issue we have here is we have the spectrum, and we have a very nice approaches to compute the spectrum, but these are all done at the moment for a static medium, and we would like to do it in dynamic medium. So the idea is that if we have a highly energetic pattern that propagates through the QGP, we would like to know the spectrum along its trajectory. For that, what we will do is we will, through a pattern, through a hydro basically, and at each point of the trajectory, we can read the properties of the hydro. So for instance, let's say that we go through a straight line in the quark-gluon plasma, and at each point we read the temperature as we have in this plot here. And then what we will have to do is go to our BDMPS formula and our method to solve this BDMPS formula and allow the properties of the medium, like the density of scattering centers or the Debye mass to vary along this trajectory. And with this, we can feed that to the code and compute the spectrum along the trajectory. But the important thing here is that the spectrum is along the trajectory. There is no something per point, so you need to go and do this along the trajectory. And actually, that's something we can do, and that's something that I did here. So I just threw a pattern in a hydro code for central collisions at the LAC, and I extract the temperature profile, and I feed that to the code, and I compute the full solution of the spectrum. This is the full numerical method that we developed. And that's something that we can do, but it takes time. And it takes time. So if we want to do this in a real calculation of an observable, and we have to do this for all the trajectories and all in the QGP, that would be not efficient, because solving this for its trajectory takes like 4 hours or something like that. So this is not something we can do on the fly. So we need to pre-tabulate this. But the problem is that, as I said, okay, the spectrum goes along the trajectory. You need to know a priori how all the medium parameters are going to behave along the trajectory. And of course, this is something that we basically don't know. So what have people think about, and this is something that was done already 20 years ago, it's like, oh, okay, I just go through my trajectory and I replace the temperature profile by its average, and I compute the spectrum for the average temperature. But this does not work. That does not work very well. And actually, we already knew this in the context of the harmonic oscillator. And what I'm plotting here is the full solution along the trajectory, doing the full numerics for a profile like this one, this temperature profile on the left, and we get this blue curve. And in purple, I just compute the spectrum, assuming that the temperature is just the median temperature along the path. And as you see, this fails actually miserably. And that's not something we want to do. We don't want to just do this all highly involved numerical calculations for the spectrum, then to spoil everything when we go to expanding media. So many years ago, people decided, okay, we have to find something already better than this in the context of the harmonic oscillator. And they developed this idea that we call scaling laws, which is the idea to find matching relations between what we want to compute, the full spectrum, and a static equivalent. So the idea is to find the values of the parameters that best approximate our dynamic spectrum, and use these scaling laws to pre-tabulate, instead of this dynamic that we cannot do, the static scenario according to these scaling laws. So for instance, here I again compute the spectrum in the blue line for the full dynamical evolving medium. And what I do is I take these scaling relations to find the equivalent value of the parameters in a static scenario. And what I found is that basically the approximation is better than the average values, but it's still not very good. And this is just a particular trajectory, but of course I have done this for many trajectories in different kind of collisions and different values of the parameters. And the errors can go up to 20%. So that's something that we don't find satisfactory enough. So we try to go and do something better. So our idea is, okay, we always pre-tabulate the static one, but why the static one? We can try to find an equivalent scenario, but that is not static, but that is given by, for instance, a power law. And why a power law? Just because it's something simple that doesn't depend on many parameters. So we have to pre-tabulate. we don't have to pretabulate for many values, for many different parameters. This is just a try. Let's see how it works. And the idea is, okay, now my real spectrum is the spectrum along the path given by this hydra that we have here. And then I will pretabulate for this profile where the medium parameters are given by power laws. And I will use this kind of scaling relations that are very similar to the previous one, but done with a power law spectrum. And that's what we are gonna try. And actually what we find is that it works very well. So we have always in blue the real solution, the real dynamical solution, and in purple we have the static one that I show in the previous plots. So same scaling law, but for a static profile. So let's put alpha equals 0 here and you get that curve. And we see that it didn't work very well. But if we do a dynamic one for a power law that behaves with, that we put alpha equal 0.5, it works very well, and that's very nice. But it could be that it's just this trajectory that I chose. So I did many different trajectories in central collisions, also in peripheral, going at different angles. And what we find is that the errors are quite low, and that's good. And actually, I even went for weird cases. So you can have cases where the parton is produced in the edge of the collision. So it goes with an angle. And in that case, the temperature first rises and then goes down. And we would expect that this wouldn't work very well because, of course, we are approximating the spectrum for a power law, which doesn't have this rise, but actually it works quite well. And the error is below the 5%. So not bad. Okay. So now what we want to do is try to do phenomenology. And like as a first thing, we can, for instance, try to compute something like the quenching factor that is like a proxy for the RAA, like the basic observables that the most basic observable we can compute. And for that, we need to compute something that we call the quenching waves, which is the probability distribution that the hard parton lose some delta energy loss. The thing is that we can compute these things, and now that we have the scaling laws, we can do it using the scaling laws for the dynamic spectrum, and that's not a problem. But when we compute these things, actually, we don't use the spectrum that I've been showing all this time, because up to now, I've been showing this spectrum integrated in KT, and what I've been doing is integrating this KT from 0 to infinite, and in that way, I get rid of the broadening, and I get a simplest expression. And actually, as you have been seeing in these plots at low energies, the spectrum diverges in this limit. But what we have to do is not integrate up to the energy, but integrate to some cutoff, because all this approach, all this BDMPS formula was derived assuming that the transfer momentum of the mid-gluon is smaller than omega. So we cannot just integrate up to infinite, we have to do it until omega. And if you are wondering why we do it like that before, it's just because in this limit is where you get the typical analytical calculations, and you can get very interesting insights on the physics. So it's a very interesting in a conceptual way limit, but for phenomenology, we need to do that. And when we do that, our spectrum now depends on an extra parameter, this R. So it's just like depending on 3 linear independent set of parameters. And when you put this limit, you get this kind of curves that do not diverge anymore, and you can use them to compute the quenching waves and then start to do some phenomenology with that. So the thing is that we have introduced a new parameter, and that means that we need to find a scaling law for this parameter. And the scaling law will be done, again, with respect to a power law spectrum, because we know that that's what it works well. And what we did is just, basically, we were doing a 0 moment here, a first moment here, and then a second moment. And actually, it works very well. And even if I do weird cases, it works quite well. The errors are below the 10% between the green curve and the blue curve. And it's way much better than using the static scaling law. And we can do very different trajectories. This is in semi-peripheral collisions at the LAC. And what we see is that the errors are good and are small, and that's good, and we can quantify them. So as a summary is that there have been many developments in the calculation of the medium-induced spectrum, and the developments are both analytical and numerical. And these numerical approaches allow you to compute the spectrum along the path with a realistic medium, but this is computationally demanding. So we need to find ways to pre-compute in the spectra. And we do this using the scaling laws. And we have found that using the scaling laws with respect to a power law scenario reduces our error substantially, and that gives us hope to do phenomenology using this kind of scaling laws. And also, of course, you can think of other approaches. It doesn't need to be scaling laws. And for instance, the people from McGill are working on a Monte Carlo approach to mimic the spectrum and try to mimic the spectrum and have this Monte Carlo approach that you can use on the fly instead of pre-tabulating. Well, the summary is we have advanced a lot in the computation of the median in this spectrum, and we have very accurate methods in a static way. But if we want to move to an evolving median, we have to find some ways of doing without spoiling all our new precision. And the point is that whatever approach we use to do that, we can now quantify the errors, and that's good. So thank you very much for your attention. And I will be happy to take any questions you have.
Thank you, Carlota. So we have a question here from Urs.
Yeah, Carlota, ciao. So you have documented a lot of nice progress, technical progress on evaluating this path integral with other potentials.
Yeah.
I have physics questions about this because we don't really know what is scattering in the medium. So clearly you have Yukawa potential in one case, you have Gaussian approximation in the other case. If you go into a strongly coupled plasma in the extreme case, you think that there is no scattering center that exposes a power law tail. You would have the Gaussian approximation. You would work with a dipole approximation and think that this reflects that physical situation. The Yukawa potential, first introduced by Jin Yang and Julashi in '93, I think, as a toy model. I think it has its only physical motivation as the extreme limiting case that gives the largest, conceivably largest effect on large angle scattering. And that brings me to the question. You emphasize a lot the precision that you achieve, but in some sense, what you develop is a tool to disentangle beyond the average color field strength, the scattering effects in the target. In other words, you should take all the approximations equally seriously, but they will inform you about the different physics signatures of media that on which this jet scatters differently. And if you do that, where would you then point to a physics observable where you can always take your dipole cross-section and the average energy loss with a Gaussian approximation is the same as for your power law, but you have readjusted the absolute strength. But do you have already a physics observer, or would you know what to look for most in this calculation, where you could say, despite of readjusting the prefactors in these calculations that are up for grasp, I see different differential distributions, and I can say if A happens, I see larger angle scattering than by a Gaussian distribution.
So, well, that's a very good question, and I don't have a very sure answer about this because we haven't done it yet. But I think first, there is one thing, and is that if you change the potential, so in these methods, you can put whatever potential, which can be well motivated or not. And already Soren and Ismail, that I think he's going to give a talk today, they found that if they put a lattice potential, the difference is huge. So they have, not huge, but is of the size of all these effects. So yes, if you, at least in an static medium, where what they do is they compute the full solution with this lattice potential and also with the Yukawa. Well, I think they use the HDL and they find a difference. So of course, the model that you use is gonna change your results. And for looking for these things, I will think that we have to do some more differential things, not just the spectrum. So at least have it in the differential in KT, and probably go beyond this soft limit. And that's something that Fabi will show today. But we are in the status of just having all this machinery working. So I don't know when we will have results that could go into the phenomenology side. And if you want to do this, at least as a bare minimum, we were thinking of using rates instead of the spectrum, because then you can try to use rate equations and try to do something more differential. But we don't have results on that yet, and I think that's going to be further complicated. And probably solving rate equations with this kind of things is going to be way more complicated than the usual one. So I don't know.
Okay, just a comment to the people online. If you want to ask a question, just raise your hand using this emoji thing, reactions thing down there. Next question is from Shinya.
Yeah, you focused a lot on numerical evaluation of this. I think the difficulty is because you're trying to do a path-length integral, which means that the eventual spectrum will know all the history of the evolution. And that is really because the hard problem. And then you can imagine that if I want to calculate like event by event fluctuation, it probably will become impossible. And also in physics sense, sometimes if you want to go beyond that, it's probably even the approach probably has its own problem, because sometimes my path length will also, the evolution of the medium along the path length will also depend on the input, the energy loss, if you consider medium feedback.
Yeah.
So in a sense, that already have some kind of problem. Why can you develop some kind of approach? It's like what the Endure has. It's sort of like stepwise approach. In order to, you have to complete the path length integral all at once.
Yeah.
Is that possible?
Yeah. So yeah, that's why we were thinking of trying to use rates, because if you think about rates are per point. So this is not something you need to integrate along the trajectory. And for us, rates is just not computing the last integral in our code. So computing the rates is not difficult. The problem of the rates is that, for instance, if you think of using the Amy rates, is that what you're assuming is that, let me see if I have a plot for that. Okay, what you're assuming in the rates is that basically at each point, you can read the static rate, the static Amy rate. And what you're assuming is that the formation time is small enough that you can say, okay, I can take the temperature at this point, and this is the static value. So we can do another approximation. And what we have found is that if you use the Amy rates, the result is not very good. So we will have to go and do and use these Caron-Watt rates, which is just the derivative of our spectrum, and we will have something that goes per point. But in that case, you always have you always need. So the problem with these rates is that these rates that are basically, this is our derivative of the spectrum. So this would be the rate. And the problem with these rates is that also depend on the time. So at some point you will have to know what happened in previous times, and you will have to find some scaling laws like that. So it's not perfect. So that depends on the accuracy you need. If you are fine with using the Amy rates and having a 20% or 30% error, that's fine. But if you want to have something more correct in the theoretical side, you will have always to do some integral and find a way of doing a scaling laws. So.
Okay, I see a few more questions, but maybe Peter first, Yassine, and then the Zoom.
There's actually a follow-up to Shinyan's question. Can this formalism be integrated into Jetscape?
Yes, if you pre-tabulate it, why not in a Monte Carlo? But we will have to find, we will have to pre-tabulate, for instance, these power law rates, and you could integrate it in a Monte Carlo. Like as you have Amy pre-tabulated, you can do that. In principle, yes.
So it'd be good to discuss offline in practical terms, but that would be very interesting to do.
Okay.
Yassine?
Yeah, I have a question concerning the R parameter, which puzzles me. I mean, always really puzzled me. So this somehow signals, the parameter R signals the breakdown of collinear approximation, right? Yeah. And you apply that parameter by cutting off large angles, right? Yeah. And this could affect, so we know that the broadening probability is classical broadening, right? It's normalized to 1. So when you put that parameter, you effectively removing particles. So somehow it's, I don't know to what extent we control that large angle approximation. And this talks and interacts with the low omega region, right? Which you somehow describe better in your numerics, right? That's where the physics, the details of the potential become very important. So my question is, which one matters most, and whether the scales, how they compare, right? The scales where the R parameter becomes important, whether it happens at larger omegas compared to the temperature scale.
So, well, yes, so you're totally right, actually. The R parameter, of course, is something like, okay, I need, like if I want to be more or less consistent with the derivation of the formalism, I cannot allow the transfer momentum to be larger than the energy, but I could put here, instead of omega, put, I don't know, A times omega and put a parameter A that allows us to be different, and that will change a little bit the curves. What I have seen is, of course, it depends on which is the observable you want to compute, but for instance, if you want to compute quenching weights or something like that, the value of that parameter, whatever it is, it doesn't make much difference, like when you translate it into quenching weights. But of course, if you want to do something more differential, probably it will have a consequence. So I guess the good solution for this is, instead of using this kind of a spectrum, using the differential in KT, but the scaling laws are way more difficult. Like, I don't know, well, I will have to try, I never tried, but finding a scaling loss for that, or finding a way of putting that in a dynamic medium, is way more complicated. So, but at least for quenching weights, I think that whatever you have, if it's something that goes to zero at the small energies, it doesn't have such a big effect when you compute something like quenching weights.
Okay, I think we can do one more. We are over time, but let's do one last question from Wei Yao on Zoom.
Okay, yeah, thank you. Thank you for this nice talk. I think it's very important that we try to use the full formula. But regarding common coupling to real medium, do you think it'd be beneficial if you develop like machine learning technique, just simply mapping a trajectory of a temperature to a spectrum? In that case, yeah. I think that will even solve the event by event problem.
Yeah, you're right. Yeah, I mean, the scaling loss is just the easiest thing to try. Like, many people did it before, so we already know where they were gonna fail, where they're gonna work, but we can think about many other techniques like machine learning. Yes, you're right.
Another application of machine learning.
Another application, yeah.
Artificial trajectories. Okay, thank you. That's a good point to stop, I think. Thanks all the speakers in this morning session. Thank you.